Hi, I'm Tom Wildenhain, a software engineer on the ONNX Converters team. I'll be talking about converting TFLite models to the ONNX format. TFLite is a stripped-down model format designed for running TensorFlow models on mobile and edge devices. The TensorFlow format has over 1,000 ops and is designed for both model inference and model training. In contrast, TFLite has roughly 130 ops and is targeted for just model inference. Models are typically trained in TensorFlow and then converted to TFLite for use on less powerful devices. The open source TF to ONNX tool can already convert most TensorFlow models into the ONNX format, but previously TensorFlow Lite models could not be converted. I'm happy to announce TF to ONNX now supports creating ONNX models directly from TFLite. Download the tool via GitHub or pip and use the --TFLite flag to perform a conversion. Direct conversion is particularly useful when a model is only published in the TFLite format, or when you want to utilize optimizations that are only present in the TFLite version of a model, such as quantization. Also, TFLite models are generally simpler than their TensorFlow counterparts, so TF to ONNX may be able to convert the TFLite version of a model even if conversion from TensorFlow fails. The conversion process itself is relatively straightforward. In the rewriter phase, we look for sets of common TFLite graph patterns that can be efficiently merged into individual ONNX ops. Next, in the handler phase, we convert the remaining TFLite ops to ONNX. Since TensorFlow Lite ops are often similar to their TensorFlow counterparts, we reuse our existing TensorFlow to ONNX logic if possible. We may need to use cast, reshape, transpose ops, etc. to account for differences between the TensorFlow Lite and ONNX op specifications. Finally, in the optimizer phase, we simplify the graph, folding constants and removing unneeded ops like cast transpose sequences that may have been introduced by conversion. One aspect of TFLite that requires a bit more care is quantization. In TFLite, quantization data, like the scale and bias values, is associated directly with the model tensors. If an op has quantized inputs and outputs, TFLite will automatically use the quantized versions of that op. In ONNX, we can do something similar by converting each quantized tensor into a pair of quantized dequantized ops. ONNX Runtime will automatically substitute in the quantized version of an op if all the inputs and outputs are quantized. The advantage of this, as opposed to writing the quantized op directly into the graph, is that other runtimes using the ONNX format can still understand and run the graph even if they don't have the quantized versions of every single op implemented. If you want to remove quantization from a TFLite model, you can use the --dequantize flag during conversion. Quantization will clip values outside the expressible range of the quantized data types, and TFLite often uses this method instead of ReLU and ReLU6 ops. TF to ONNX will use the range of the quantized tensors to automatically detect and reinsert the removed ReLU and ReLU6 ops. That's an overview of TFLite to ONNX conversion. Please check out our GitHub page to try it out. This is new, so if you get a message that an op doesn't have a conversion yet, please open a GitHub issue and hopefully we'll add a conversion for it soon.
Thanks, Tom. My name is Scott McKay, and I am the ONNX Runtime Mobile Technical Lead. I'd like to give you a quick introduction to ONNX Runtime Mobile. ONNX Runtime Mobile is a variant of ONNX Runtime that minimizes the binary size for usage in mobile and edge scenarios. It utilizes the same codebase as ONNX Runtime and has been available since last year. In order to minimize binary size, we include only the required operator kernels in the build to satisfy the models that you wish to deploy. Additionally, you can reduce the types supported by these operator kernels for further reductions in binary size. A custom format is also used for the model file. Runtime usage of ONNX Runtime Mobile is the same as regular ONNX Runtime. The C, C++, Python, and Java APIs are available. We also support an NN API execution provider on Android and a CoreML execution provider on iOS. The ONNX Runtime format model is created from an ONNX model. A Python script will handle the conversion, and during the conversion, a number of things happen. The ONNX Runtime optimizations are applied, such as constant folding, and nodes are assigned to kernels. There is no ONNX schema dependency, which results in a significant binary size and memory usage saving. The ONNX Runtime format model uses Google Flat buffers for its format. When selecting the operator kernels to include in a build, a configuration file is used. The model conversion script can automatically generate this configuration file from the models you convert, or alternatively, it can be manually created and edited. As you can see from this example configuration, the syntax is quite simple with the domain, the offset, and the operator names. You can also limit the types that operator kernels support. Again, the model conversion script can automatically detect these types and generate a configuration file with them. Or alternatively, you can specify a global list of types to support. When using model-based type reduction, you will generally see a reduction in the kernel binary sizes of between 25 and 33%. At a high level, this is the ONNX Runtime mobile usage. You will take your ONNX models and put them in a directory to run the conversion script against. They will be optimized, and an optimized ORT format model will be produced, along with a configuration file that contains the operators that are required and optionally the types that are required. This configuration file is used to build the ONNX Runtime package, which is then deployed to enable inferencing on device. There are a few choices that can be made to determine the binary size. The operators and types to include will make the biggest difference, but whether you choose to enable exceptions or support for traditional ML operators or use a shared libc++ on Android will also have an impact. As you can see here, the binary size for a build with the operators required to support MobileNet is well under 1 megabyte. If we enable the reduced type support, we'll get a 31% reduction in the size of the kernels, and that package would have a size of 325 kilobytes when compressed in the Android archive that you would use to deploy your app. NNAPI usage is possible on Android. Based on the device capabilities and whether NNAPI is available, the model execution will dynamically adjust to use NNAPI where possible. If not, it will fall back to using the CPU execution provider for node execution. Finally, for any questions or feature requests, please reach out to the ONNX Runtime team via GitHub. Thank you.